Okay, so I guess it's about time to get started. Thank you all for coming on a sunny day to our second to last section. So I have, I guess, one quick announcement, which is having done sort of the experiment with the flipped classroom for sort of the section on concurrency over the past 2 weeks. One thing I learned is I should definitely pull for a better classroom. I think we all like being in, most of us at least like being in the CS department instead of up here, although I do like getting outside on sunny days. The second thing is we would like to, we are going to, not just like to, we will ask you all to complete a survey, sort of a standard, online survey asking what you thought of the concurrency piece. And the reason is we want to know, how did this compare to the normal way that I teach the course? What are the things that could go better? Clearly the quizzes started out kind of rough and got better, I hope. And so the last question is really, is this something we should keep pursuing, or should we go back to teaching things the normal way? And so I think linked to the Moodle page is the link for the questionnaire now that I'd like you all to fill out. And as an added bonus, it's going to be counted as another quiz, the fact that you fill it out. It is totally anonymous, so we don't know who did it, but we can track that it has been done. And so we will use that to incentivize you to actually give us some feedback. Are there any questions? Yes?
Next week, are we going to be in there again?
I'm going to try to reserve back there for all 3 dates next week, because I really like it there. So I'll see what I can do, and I will send out mail soon. So one other quick notice is I am out of town on Tuesday, so there will be a graduate student lecturing. He's a pretty good guy named Tyler Harder, who's an undergrad here, went through this course and started working with one of the other professors and went on to win the Best Paper Award at the premier conference on operating systems in his first year of graduate school. And he works in the area file systems, and he'll be talking about distributed file systems like AFS and NFS. And sort of explain how do you make a file system work over a network. So hopefully that should go well. So then today and tomorrow I want to talk about virtualization of virtual machines, which I think is an interesting topic that we haven't gotten to yet. So before I go on with how virtual machines work, are there any questions? Yes?
Is there a quiz for class tomorrow?
No. So we are done with the flipped lectures. We're back to normal lectures. It sounds like you like the videos, perhaps. So one of the reasons is it takes more time to prepare the videos. So I kind of wanted to experiment and see how they work and get some feedback before making the whole set. And the other thing is that the nice thing about the concurrency stuff in a way is there's this very natural set of problems to work on in class to sort of try writing code. And for the rest of the material, I haven't quite figured out what to do in class other than lecture more. And I really don't want to use this flipped classroom as a way of packing 30% more material into the course, because you get lectures at home, you get lectures here, and so you just get a much, much bigger, denser course. So that's why I haven't gone further yet. Hopefully in the future, if it all works out, then I will do more and more of the course as time goes on. Any other questions? Okay, so in case you're wondering why my computer's open, it's just so I can record this for the people who can't make it to section. Okay, so no other questions. I'm going to be lugging this thing around, I guess. So what we're talking about now is virtual machine technologies. And the key motivation is, to some extent, that wouldn't it be nice to run more than one operating system on your computer at a time? So normally if you want to use, say, both Linux and Windows, the old way you would do this is you would install both, and then you could choose when you turn your computer on, do you boot into Windows or do you boot into Linux? And if you want to switch, you have to shut down, reboot, and choose the alternate one. And then sometimes you can access files from one to the other if it's compatible. Generally from Windows, you can't really access your Linux files. So it gets a little bit ugly. But this seems like a really great thing to do. So for example, what if you're sort of an OS developer and you want to debug an operating system? currently, or the way it did when I started doing my work was you'd have two computers, one to put your prototype operating system on, one which would be your compiling machine and debugger. You connect them with a serial cable, and then use the serial cable to send debugging commands back and forth. And it's a huge hassle, and it's very brittle, and things you can't debug things like interrupts. And interrupts are kind of a huge source of problem. Another reason you might want this is isolation. So suppose you're the kind of person who likes to go to random websites and download random binaries and try out all kinds of programs, and you're very experimental in what you do on the web. But at the same time, you want to do online banking. And you really want to make sure that none of the malware you download will get access to your bank account. So wouldn't it be nice if you can say, I want to have an isolated environment where either I'll run my banking web browser and I won't do anything but banking, so there should be no malware, or I'll have an isolated web browser where I run my experimental stuff and then it's isolated from the rest of the system. So the challenge here, the reason you might want to do this is most people think that operating systems on their own don't really provide enough safety. If you want to do sort of unsafe things and safe things on the same computer, an OS can't really handle that very well. Mostly because operating systems for 30 years are really built to share things really well. You can both share files, you can do IPC. You know, the scheduler sort of gives more time to whoever has more threads. So there's lots of things that make the OS really great at sharing things, but not so good at isolation. So if we have two operating systems, each operating system can do things on its own. They don't share anything. Another reason, as I mentioned before, using other operating systems. So we have a problem in our department for graduate students. If you are one, you'll know what I mean, which is that most people want to use Linux for their research because you've got the command shell, you've got GC, all these great things. But when it comes time to do presentations, you want to use PowerPoint. And there is no PowerPoint for Linux. And so what do? You know, you can have a laptop that runs Windows and do your PowerPoint on your laptop and do Linux on your desktop or something like that. But wouldn't it be nice to sort of run Linux most of the time and then run Windows on top of Linux some way so you can run your Microsoft application? So, does anybody disagree? Alfred?
I just want to add that virtual machines these days are used mostly also for like when you sell an enterprise software that has many modules, database, middle tier, clients, and a customer wants to do a prototype, and they don't want to go through the hassle of installing all the pieces. You usually send them a VM that has everything, and you can just do some preliminary testing on it.
All right, so one thing, if you have something that might sort of take a lot of installation or run on multiple machines, but you don't need to handle load that you would need 5 machines, you could run all 5 separate pieces on one machine using virtualization. So why can't we do this? So if we wanted to make it possible to run more than one operating system at a time, why not just make this a feature of operating systems? And before you say it's impossible, I have reviewed papers where people have indeed done this, and they can run 2 copies of Linux side by side on the same computer with no virtualization technology whatsoever. You can do anything in software. But why? What is it about operating systems that makes it hard to run more than one? We can clearly run more than one application at a time. Why can't we run more than one operating system?
Operating systems like they expect to have exclusive use of the computer.
So, when you say computer, can you be more specific? Okay. So, we sort of know how to share a processor using time slicing. So, what if we have a timer, and when the timer goes off, we just switch operating systems? Somebody over here.
Well, like if you have like keyword stuff, it doesn't know what operating system to send it to.
Okay. So we have a problem where so I'll abstract that to devices. That operating systems have device drivers that talk to devices, and the device drivers really expect that they own the device and no one else is working with it. That they'll send a command to the device and then pull for an answer to come back or do DMA. Or they'll send a command to the device and then pull for an answer to come back or do DMA. Or they'll send a command to the device and then pull for an answer to come back or do DMA. Or they'll send a command to the device and then pull for an answer to come back or do DMA. And if somebody else is trying to use the device at the same time, it'll get hopelessly broken. So devices are bad. Other things that might not work. Yes?
Isn't it a problem to determine who has a higher privilege when it comes to dealing with...
Well, maybe they're both equal, so we don't have to worry about who has the higher privilege. But that would be a problem. Other things that could be a problem. Yeah, Scott.
Memory.
Okay, so when you turn on your computer, the operating system asks somebody how much memory is there, and it says, thanks, I'll take it all. It doesn't say how much do I get, it just says, I assume I own all the memory, I'm taking all of it. This is what databases do, by the way, also. When you install a database, they basically take all your memory. So if you have two operating systems, they're both going to say, can I have all the memory, and that doesn't work. So this is something we could probably fix fairly easily because memory is pretty easily divided. When you boot one operating system, somehow we could lie to it, or we could modify it to say, I'll take half the memory, and the other one could take half the memory also. So another thing in here are interrupts. So when interrupts come in, they have to go to a software handler, and that handler responds to them somehow. And they come right from the hardware, and the hardware only knows how to deliver interrupts to one specific handler. It doesn't know that there could be two operating systems that want interrupts from a device, and so it will always go to one operating system. And so it's very hard if you want to have devices that generate interrupts to make sure that the right interrupt goes to the right device. The takeaway is you could probably pull this off by heavy modifications to Linux or Windows, and you could probably make it work for two operating systems, but making it work for Linux and Windows at the same time, given the modifications you would need to solve interrupt problems and memory problems and CPU problems, would be difficult. Okay, so we can agree it's bad. It's a bad idea to do this in the operating system. So, any other thoughts on how we could do this? Is anybody here a computer engineer? A few people. So one thing so when people are designing new processors, they're effectively running a separate processor on top of your regular processor using a simulator or an emulator. So one way to solve this is to say, we'll run one operating system normally, it has complete control of the hardware, but to run other operating systems, what we'll do is we'll basically build a simulator of a computer. It'll have a simulator for a processor, perhaps a simulator for devices that we need, and we'll implement it all in software. So you might have some code that looks like this. This is real code from a real simulator. So the key thing you do in a simulator is you take every instruction the processor supports and you write a function that implements that instruction. So this is the function to add a register A0 to the stack segment, and it just sort of updates A0 to add in the stack segment value right here, in case you can't read. So we're just saying we're going to implement whatever an instruction does as a function. We will then implement decode to basically say something like, whoops. So we'll basically take an instruction, do what a real piece of hardware would do, pull out the opcode, and then have a big case statement that says for every opcode, call the function that does the right thing for this opcode. So this allows you to simulate a complete processor in software, and computer architects designing new processors do this all the time. So this is totally doable. And the nice thing is you can do any processor you want. So you could emulate an ARM processor on x86. You could do PowerPC on x86. So as an example, when Apple moved from the 68000 processor to the PowerPC processor, they wrote an emulator that basically executed 68000 instructions on a PowerPC instruction set. When they did it again to go from PowerPC to x86, they wrote another one that would run PowerPC operations on x86 using technology like this, where you just emulate what the native processor would do. So this allows you to basically emulate a whole system. So you can boot up Windows or Linux inside this system, and then you can install applications and run it. So there's a free version of this called QEMU. Has anybody used QEMU or heard of it? Some people have. So it's written by this guy, Fabrice Bellard, who also wrote an x86 emulator like this in JavaScript. So there's a website you can go to that runs an emulator where you can do things on an old PC, I guess. So this works totally fine, and you can run multiple operating systems now by emulating a complete system. So what is the problem with this approach? Kaushik.
Your operating system might take a few hours to boot.
Right. So the key challenge with this, I think you're getting at, is performance. That where normally you'd execute one instruction per cycle or something like that. Now for every instruction, we've got some code to do the decode. We've got some code that has to actually emulate each instruction. So each instruction might take 10 or 100 native instructions to execute. So it's very slow. So this typically gives you about a 10 times slowdown. It's not, won't take, unless your computer is really slow to boot, it won't take hours and hours, but it is pretty slow. So the next obvious question is, how can we speed this up? What are some obvious things we can do? Yes?
Instead of using like a normal emulator, try do something new and crazy like just-in-time compilation.
Okay, so that's definitely something we can do. So here we're calling a function for every instruction that we're emulating. One thing we could do is we could basically parse ahead, read ahead the next 10 instructions, figure out what they do, and then sort of generate native code that will execute those 10 instructions as one big chunk. This, by the way, is what this is what VMware does in some cases. This is sort of how Java virtual machines work. That they have, Java virtual machines have their own instruction set, but it runs in x86. And so inside the JVM, there is code that looks like this that says for every Java instruction, here's how to execute it. And to make it faster, they exactly do that. They pick certain sequences of code, and they'll convert the whole thing into native code at once. So that works. It's very complicated, though. And there's a problem of what if you have an instruction that takes a TLB miss in the middle, or some kind of exception. So now you have to worry about, when you take an exception in the middle of this chunk of code that you compiled, how do you sort of get the state of your emulated processor back to the right place? So you can do this, but it ends up being pretty complicated. But one of the things that people observed is, we've got this device that can execute instructions really quickly. Like if we are emulating x86 on x86, we have a really fast way to execute x86 instructions, which is called the processor. So what if we just say something like, so one thing we can do is we can say if we're implementing an x86 instruction and we're running on an x86 processor, let's just use the processor to directly execute the instruction instead of writing a version of it in C. So this is one step, which means one, we don't really need to know what this instruction does because the processor will just do the right thing. And second, it'll be a lot faster because now we're executing this in as fast as the machine can possibly do it. So the core idea here is we're going to basically use the processor to execute the instructions directly instead of emulating the instructions. Okay. Let me just check my notes. So, in this case, we did it just for a single instruction, but as you suggested, we can do it for whole sequences of instructions. So, instead of emulating just one instruction, why don't we run a whole set of program instructions at once? So the basic idea here is we are going to instead of emulating most code, we are just going to natively execute as much code as possible. So we will use the processor to execute whatever code we can. So one thing we can observe is, remember when we talked about user mode processes and user mode processes, we said that processes sort of have they have the view that they are running in the computer all by themselves, and the way they interact with anybody else is through system calls. But they can't directly interact with devices or with other processes on their own. What that means is that we can actually run pretty much all user mode code natively, because we can just load into memory whatever code and data the emulated machine wants to use. We set the instruction pointer to the code we should execute and let it run, and it will just run through that code natively, and it doesn't care really what the operating system is doing because this is just user mode code. We really just need to worry about what the operating system is doing, because user mode code already has a view of a virtual processor. It can't see privilege registers, it can't see devices, it can't see physical memory and things like that. So this is the essence of virtual machine technology, is that we are going to somehow emulate enough of a processor to run an operating system on it. And we are then going to let user mode code in this other operating system run natively, and then we'll sort of use this emulated processor to run the operating system. And this will let us run multiple operating systems on a single computer. And so what's difficult is really, the challenge here is really making that simulated computer that the operating system is running on go as fast as possible. So the picture that we end up with is something where we have sort of the CPU and hardware at the bottom. We're then going to have this layer called the virtual machine monitor. And the job of the virtual machine monitor is to implement this sort of processor emulation or simulation that allows multiple operating systems to run. And this sort of emulated computer we're going to call a virtual machine. So then on top of this, we can have sort of multiple virtual machines. And within each one of these, we can have an OS. And then we can run applications on top of it. And all we're really doing is sort of emulating a complete system in software that sort of tricks these operating systems into thinking they're running on native hardware. And anytime they want to do anything privileged or they need the operating system, we're going to have this virtual machine monitor sort of do the right thing or emulate the real hardware in that case. And we'll talk about exactly how that works. So any questions so far? So one thing that's interesting is that this idea was actually invented around 1967. What happened was IBM was selling mainframes, and their mainframe operating system was a batch operating system. It didn't support time sharing. So you could submit long-running jobs, they would run, you'd come back an hour later, you get your response back. But you couldn't type at a keyboard and interact. And users got frustrated by this, and so what they did was they wanted to say, well, we need your operating system, the IBM operating system, to run certain software, but we want to run our own operating systems also. And so they wrote this virtual machine monitor layer that let them run both the IBM operating system and time share it with other operating systems. So they actually put the time sharing where you switch back and forth down here. This was really popular in the early 1970s with mainframes. It then disappeared until about 1998 when some researchers at Stanford had the idea that you could use this in big servers. If you have a server that has 128 processors, you could use this to carve it up and give this operating 100 processors, and this one 20 processors, and this 8 processors. So you could take a big server and carve it up into a bunch of small servers, and then you would have it would be like having many servers, but a much smaller box. And from that, they went and founded the company VMware, which is now a multi-billion-dollar company. And so this idea was sort of absent for about 20 years, and then came back because of these Stanford professors. So it's sort of a best case result, I think, for academic research, perhaps. Okay. So the questions here are really, how do we sort of make all of the resources available to the operating system? So how do we create a virtual CPU? So the way we can share a processor between multiple operating systems is that we can basically time slice it. We'll run one operating system for a while, we'll then stop running it, switch to another operating system for a while, stop running it, switch to a third operating system. And the virtual machine monitor here acts like an operating system with scheduling and timer interrupts and all those things. So the CPU is pretty easy to share between different virtual machines. For memory, so memory, in a way, is also easy to share. We're just going to take physical memory, and the virtual machine monitor will carve it up and give some physical memory to each of the operating systems. And so each operating system will have a fraction of the total memory in the system. So this is also pretty a straightforward idea, but we'll see there's some implementation challenges. If we have devices attached to the system, how could we deal with devices attached to the system? Any thoughts? So like a network, a disk, something like that. And we'll go into more details on exactly how to do it. David?
I guess the format where you can share it through Virtual Bridge. For device, you can assign them for VM.
So for people who haven't used VMware before or VirtualBox, what is a virtual bridge? Or do you like me to explain it? I mean, clearly you know how this works, so perhaps it was a leading question. But the basic idea here, I'll jump in for you. The first thing to do is to emulate the device in software. So for a network card, the way you interact with a network card is through programmed I/O, memory mapped I/O, I/O ports, and we basically will emulate. So we will emulate the device. So if a driver will sort of write some data to the device, we'll write an emulator that will pick up that data, recognize the OS is trying to send a packet, and then turn around and call the real network driver. So we will sort of have a real driver for all the devices that runs as part of the VMM, and then we'll have an emulator for the device that runs in the VMM that sort of detects when the operating system wants to use it and translates what the operating system is doing back into requests to the real device. So this is sort of the essence of how you virtualize sort of the three major components in a system. And I now want to sort of get into some of the more nitty-gritty details. First, a bit of terminology. Got my phone going on. Okay. So first of all, a virtual machine or a guest VM is really this sort of emulated computer. It is sort of the, when you're running the operating system, it looks like a real computer, but it's implemented in a mix of hardware and software. So this is just terminology. The guest operating system is the operating system running inside the virtual machine. The virtual machine monitor it implements a hardware interface. So we talked about an operating system has an interface where you can invoke the operating system and ask it to do things, and these are called system calls. A virtual machine monitor similarly sort of manages hardware. It has an interface to request that it do things, but the interface that implements is the native hardware interface, x86 instructions, or I/O operations to talk to devices. The basic way the VMM is going to work is that all instructions that reference any kind of privileged state that only the operating system can reference, such as I/O memory, page tables, any privilege disabling, enabling interrupts, all of those instructions will be executed to refer to a software copy of that hardware state. So because we're emulating the hardware, all these privileged things will operate on the emulated software copy of the hardware. And all references to specific physical resources are instead executed against virtual resources. So instead of having sort of a physical CPU where you execute privileged instructions, instead we will have a virtual copy of the CPU where we emulate somehow those privileged instructions on this virtual copy of the CPU. Similarly, because interrupts come from real physical devices, they can't be handled directly by the operating system, because then the operating system would refer to a specific physical device. Instead, interrupts from physical devices, interactions with the outside, all go to the virtual machine monitor instead, and the virtual machine monitor can then emulate that interrupt if it wants by telling its virtual CPU to have an interrupt or something like that. So one thing we need here is we don't want these operating systems, these guest operating systems, to be able to see the memory in use by the virtual machine or to modify the virtual machine monitor at all. So what this means is that much as we don't want processes, user mode processes, to modify data in the kernel, we don't want guest operating systems to modify code and data in the virtual machine monitor. So we need sort of the guest operating systems to run at a lower privilege monitor than the VMM, so they can't modify the VMM. The VMM runs at a higher privilege level than the guest, so it can sort of see whatever the guest OS is doing, and it can provide these privileged resources without getting locked up. So one thing to note is that in many ways, a virtual machine monitor is a lot like an operating system because it has to manage physical resources. It has to manage memory, devices, the CPU. The major difference is that it doesn't really abstract devices. It doesn't take a disk and make it look like a file system. It doesn't take a CPU and make it look like a process. Instead, it's just doing the management and scheduling and allocation, but it's not really doing abstraction anymore. And for that reason, a VMM is typically much smaller than an operating system because it just has the low-level routines to manage things and not the high-level routines that sort of abstract them into fancier features. Okay, so the basic layout of how we're going to do this and what a VMM is and does, fairly clear. Yes.
I'm just a little confused. So the virtual machine monitor is even the host OS runs on it?
So in this picture, there is no host operating system. So we will talk about later different models, but here there's not necessarily a requirement that you have one operating system which sort of runs natively and other ones which are guests. We're just saying there is some piece of code that runs here that shares the CPU and hardware between multiple operating systems. And we'll talk about the difference between this kind of picture and the idea where you have a separate host operating system later.
So interrupts go to the
So
virtual-
interrupts would come from the hardware into the VMM. The VMM could then look at the interrupt and say, oh, this is a network packet for Linux, so I'm going to inject a virtual interrupt into this virtual machine here. Linux will then get the data and then hand it off to the application.
How there's more than one Linux?
Well, I said Linux just to name this, but it basically, each of these has some identity. It'll say, oh, this is, this is the specific one that should receive the packet. So it has to have some way of looking at a packet and saying, who does this go to? And once it figures out who it goes to, then it can do this delivery. Yes?
So how does it know, like, which one to send it to? Like, if you have, like, keyboard, like, keystrokes and you have, like, Word open on multiple OSs, how does it know, like, which one to send it to?
So the answer to most of these questions is the same way an operating system knows. So if you have Word and Excel and PowerPoint open on your computer, how does Linux or Windows know where to send keyboard input?
Well, that's the one that's, like, in the foreground.
Right. So the same exact thing happens, but if you use this and you have a device that really you can't share easily, or the keystrokes don't say who they're destined for, then you have to have some mechanism of designating from the VMM which one of these should get the keystrokes. So if you use VMware, for example, it will typically take whichever window's in front, and it will send your keystrokes there. So it does exactly the same thing. The thing is that the other devices like a disk and a network don't have that property, because network packets come with an address in them of who they're supposed to go to. So the address of the network packet will let us choose which of these 3 VMs. And with disks, disk data never comes unsolicited. You always ask for some disk data and then get the response, or you're writing some disk data out and asking for acknowledgement. So in that case, you always know there's sort of a matched pair of request and response. So there's no ambiguity as to who gets the data. Is that clear? A little bit. We'll go through this more, so it'll become more clear. Any other questions of the high-level picture? Okay, so the basic picture we have is we're going to have a VMM. We said that we can natively execute user mode code because user mode code just does normal unprivileged things. It doesn't touch any privileged state, so that's really easy to just execute by setting up memory properly. So the challenge is, what do we do with privileged state? How do we emulate the process? So one option is to just, whenever you're in privileged mode, turn off direct execution of instructions and just emulate the complete CPU. So switch to this mode we talked about earlier where you look at the instruction, figure out what it does, and then dispatch it. This was used by the virtual PC product that Microsoft sold for many years. User mode code would run natively on the processor. Everything in privileged mode would run on a processor emulator, and you'd switch back and forth. I don't need to ask you, the downside of this is you make your operating system run 10 times slower than it should. So it's better than nothing, but it's still pretty bad. Option 2 says, well, the real problem is not normal code running in the operating system. It's when you actually run privileged instructions. So remember, the operating system has a lot of normal code that does things like load data from memory, store data to memory, add things together, look things up in tables, and a very small fraction of it actually talks to hardware. It's when you set status registers, when you program an interrupt vector, when you do I/O, these all talk to hardware. But most of the code is just manipulating data structures. Remember, I always say, there's a data structure for that. For everything we talk about, there's a data structure. So our idea is we're just going to actually run the operating system on the processor, and every normal instruction will execute perfectly fine. But then we want to trap any privileged operation and emulate it on our virtual hardware. So a simple way to do this is to run the operating system in an unprivileged mode. So instead of running the operating system in the privileged mode of the processor, we run it in an unprivileged mode of the processor. And we already said, if you execute a privileged instruction and you're not in privileged mode, it causes the processor to trap. So the processor will actually tell us every time the operating system does a privileged instruction. So what we effectively do is we run both your user mode code at user mode and run the operating system at user mode. The operating system just runs along fine using its normal instructions whenever it wants. When it happens to do something privileged, it'll try to execute the instruction. The CPU will trap and say, this program just sort of tried to execute a privileged instruction that's illegal. Tell me what to do. The VMM will catch that trap, have a handler that emulates that instruction on this virtual copy of the hardware. That's why it's called trap and emulate. We trap privileged instructions, we emulate them in software inside the VMM. And the VMM has sort of a complete copy of whatever hardware that privileged state would refer to. So practically speaking, Windows has 4 levels of privilege. So what people do in Windows, normally ring 0 is the most privileged mode, and the operating system normally runs here, is they now run the VMM in ring 0. They run the kernel in ring 1. And then they run user mode code in ring 3. And only ring 0 is privileged. The other rings are not privileged. And so any privileged instructions executed out here will cause a trap down to here. So we can now, anytime a kernel does something, tell that it's doing something, emulate it, fix up the registers, return from the interrupt, let the kernel keep going, and it's happily running, thinking that it's on a real processor. And as long as it keeps executing normal instructions, it runs up here. It's only in privileged instructions that it drops down here. So that sounds pretty straightforward, right? We're basically using the processor to emulate itself, in a way. So, are there any questions? There's a problem with this model. This was great, and this worked really well back in like 1973, but it doesn't actually work. So, we said that privileged instructions are guaranteed to trap into the operating system when you run them, which is fine. What if we have an instruction, something like an instruction that says, am I currently running in ring 0? So this instruction, you could execute anytime, and it'll tell you, yes, I'm in ring 0, I'm in privileged mode, or no, I'm not in privileged mode. With this instruction, the operating system, if it used this instruction, could now tell, am I running on real hardware, or am I running in a virtual machine? And then it might do something different. It might, decide not to run. What we would like is we'd like the hardware to act exactly like real hardware. And the problem with this instruction is that it behaves differently in different rings, but it doesn't, instead of trapping, it's not strictly privileged or non-privileged, it's a hybrid because it's one instruction that has different behavior depending on when it's called. Let me just see if I have the terminology. These are called sensitive instructions. So, this example is a little silly because the kernel wouldn't normally call this. But there's other instructions that the kernel might use and depend on having the behavior of privilege mode that are also used by user mode code, where user mode code depends on it having a different behavior. So a standard instruction example of this is the popf and pushf instructions on x86. x86 has condition codes. The condition codes are stored in a flags register. The F here is for flags. There's also other condition codes that are stored in the flash register. So, for example, the state of whether interrupts are enabled or disabled is actually 1 bit in the flags register. So the interesting thing is this flags register is used at user mode to be able to check your condition codes to see, if you do a comparison, what happened. And in the kernel, it's used to enable and disable interrupts. So we now have an instruction that behaves that has sort of different uses in user mode and kernel mode. In kernel mode, one of the things you can do, so pushf takes the current flags and pushes them on the stack. Popf takes the value at the top of the stack and puts it into the flags field. If you do this in kernel mode, it will save and restore the state of whether interrupts are enabled or disabled. So if they were disabled and you call pushf, it'll save the fact they were disabled. When you call popf, it'll remember they were disabled and disable them again if you had modified it in the middle. In user mode code, the popf basically ignores the disabled interrupt flag. So if you try to disable interrupts in user mode, it doesn't cause a processor trap. It just ignores that and pops all the other flags. So this gives us different behavior in user mode and kernel mode. So suppose we have kernel mode code that is trying to disable interrupts by pushing the flags onto the stack, clearing the interrupt flag on the stack, and then popping them back into memory. So we push I equals 1, we then set I equals 0, and then we pop off interrupts are now turned off. In the kernel, this should disable interrupts. If we run this in this trap and emulate model, what will happen? Well, the problem is the kernel will be trying to disable interrupts, which is a privileged operation, but the instruction that it's using is one of these sensitive instructions that doesn't trap. So the kernel has done something that the virtual machine monitor has to know about, but it doesn't cause a trap, so the virtual machine monitor doesn't learn about the fact that it didn't trap. And so this would make the kernel run incorrectly because the VMM could still send virtual interrupts to the OS, causing it to do the wrong thing. So what this means is that people sort of classify architectures that have this behavior as non-virtualizable architectures, meaning that you can't just run a VMM using trap and emulate. And x86 has half a dozen instructions that have this behavior, and this is one reason that virtual machines were not used with x86 for 20 years, because they were put in the non-virtualizable category. So we will stop here on the cliffhanger of how you solve this problem, and tomorrow we will pick up and see 3 different solutions to this problem, and keep moving forward.